This is part 4B of estimating existing sprinkler design. I decided to split them up into two just to decrease the overall length of this presentation. As I've indicated in all the other prior videos, it's for entertainment purposes only, and you don't make any final decisions or changes to a system without a full set of hydraulic calculations. This is the Hayes and Williams formula for friction loss. This is in PSI per foot of pipe. And I just want to emphasize 2 points. One is flow. So flow is the Q. And just to kind of simplify things, if we square the Q, it has a dramatic impact on the overall friction loss. So for instance, a flow of 2, you square that, that's 4. Not a dramatic increase, but you square a flow of 20, it becomes 400. So Q is going to be an important consideration in determining the overall friction loss. The other thing is pipe size. And that pipe size, just to kind of round it off, let's just say it's diameter to the power of 5. And if we had a diameter of 2 inches to the 5th power, that would be 32. And a diameter of 6 inches to the 5th power is 7,776, roughly 25 times more in size than a 2-inch line. And since that's in the denominator, it makes the overall friction loss less. So we need to be cognizant that the larger diameter pipe will result in overall lower friction losses. The C is, of course, it's an unknown. Be quite frank with you. I would just say to play it safe, use the numbers that have been established by NFPA. The 120 for the wet, 100 for the wide, use 100 for the underground, and don't try to. And if it's other than plastic, and don't try to be coy and don't try to be cute. The actual C is probably not those numbers, but as long as you use what the code provides you, then you're in, I think, probably the best position. Just as a way of refreshing, this is the Excel table. If you recall, there's a matrix for the 235 system, the 123, and the 125 system, and we're going to compare the three systems for roughly equivalent systems: a center-fed 8-head system with 10 by 10 space and 10 by 9 in the case of the 125 system. I do want to make one comment about these matrix and these numbers here. I don't know that they're accurate. I know that they were developed for a major insurance company. I spoke to someone who's a kind of a trusted person, and they'd used it out in the field for many years. But I don't know that all these numbers are correct. And that's why I continually come back to the point that at some point you're going to need to do hydraulic calculations. There's just no way around it. Even on that 55-page FM 2-76 document, I don't know that they're all accurate. And I certainly wouldn't base my professional engineering stamp based on something that I haven't calculated out. But that doesn't mean this doesn't have some usefulness, as you'll see in the upcoming slide. I want to make a comparison of the systems. I've got a grid here, matrix with across top systems spacing, and then these OH2, EH1, and EH2 with these various numbers across the top. So let's just start with the system 1, 2, 3, and we discussed what that was. It's a one pipe supplying 1 3/4 inch pipe supplying a head, and then 2 to the 1 inch, etc. And we have 10 by 10 spacing, 10 feet between lines, 10 feet between heads. This concept up here of OH2, EH1, and EH2, and OH2 is a, and I'm going to discuss these in an upcoming video, would be a combustible, a moderate combustible type occupancy, machine shop, something of that sort. The EH1 would be a higher combustible content with little or no flammable liquids. It might be a printer or a wood shop, something that had some kind of fuel loading there. And then an EH2, extra hazard 2, would be moderate flammables or combustible liquids, and also plastic processing and solvent cleaning, that sort of thing. So let's just take a look at the requirements, the gallon per minute requirement and the pressure within that 3,000 foot design area. We're going to go over design area when we start to cover hydraulically calculated systems. So for the 1, 2, 3 system, within that 3,000 square foot area, we need 786 GPM at 41. And so you can see with the larger piping of the 2, 3, 5 system, we're down to 731 at 36. We need less water and we need less pressure. And then with the 1, 2, 5 system and the much larger piping, we only need, again, the spacing is 10 by 9, but for the purposes of this, it's not going to make that much difference. We need 651 gallons at 22, a considerable difference between the 786 and the 41. So that's at this kind of combustible, moderate combustible loaded occupancy. Then when we start to get to these higher combustible loadings, you can see that the 1, 2, 3 systems, to meet that 0.28 over 3,000, which we will discuss, requires a 1294 GPM at 105. The 235 requires 1204 at 85. And the 125 requires 1101 at 54. So what it's saying is that this doesn't even include the water being provided back to the riser or the elevation losses we would incur as well, that we need a considerable amount of water at a considerable pressure when we have these small piping systems of a 1, 2, 3 or a 2, 3, 5 system to meet the demands of a high combustible content loaded occupancy. And you can see the difference of in the 125 and the 123. It's a 50 psi difference in pressure. It's considerable. And then if the EH2 things just blow up on the 123 and the 235 system. For the 123 to achieve a 0.38 over 3,000, you need 1756 at 180. 235 was 1634 at 150. Those are really pressures that you're not going to see much. If you do see them, there's some kind of extraordinary situation. You're just not going to see that very often. And even the 1471 at 97, that's doable. That's a pretty beefy sprinkler system. And again, that doesn't include friction losses back to the base of the riser or elevation losses as well. So we have some, we can make some judgment about these systems now that we've had a chance to come up with some rough numbers as to what the system will require for adequacy. These are the conclusions that we come up with when we look through the systems. If we have a 1, 2, 3 and a 2, 3, 5 system, those older pipe schedule systems with smaller piping, they're likely adequate for ordinary hazard occupancies. If you've got a decent water supply, they may be able to deliver an extra hazard 1 adequacy with the extraordinary water supply, be able to adequately handle an occupancy like a woodworking shop. But they're unlikely to do an extra hazard group 2 with any kind of flammable. So you look up at the ceiling, you see a 10 by 12 spacing on a 2, 3, 5 system, and you're walking through a shop with solvents, disregarding any kind of storage requirement. it's a pretty good bet that the sprinkler system is not going to deliver even if you've got 100 psi at the riser. The 125 system is likely to be adequate for the OH1, the ordinary hazard 2, the low combustible occupancies, and the high combustible but little and no flammable liquids. The 125 is up for the challenge of handling that. And then the H2 with the 125 and their demands of 0.38, the densities of 0.38 over 3,000. That's going to be it's going to be a challenge for these systems to meet. Um, I, I think we're going to do an actual sketch of a system and a calculation of using the matrix and uh, taking the friction loss through the pipe back to the riser and including elevation loss. I want to state something right up front, and I've stated it in every presentation. You need to ultimately deliver hydraulic calculations to prove your case to make any kind of change to a system. If you came to me with the back of an envelope calculation and this matrix, my first response would be to shake your hands, cut you a check, and fire you. And then I would tell all my friends in the other business to fire you as well, because this can't be done. You can't be making these kind of determinations, especially now with the availability of software for people to make significant changes to a sprinkler system without doing the calculations. But that doesn't mean that what we've just gone through in these past exercises doesn't have some relevancy. What you're doing is being able to look at a system, make a rough judgment as to where you stand and what needs to be done, and prioritize the work. So you go into a system that a facility that's got a 235 pipe schedule system. They're doing some kind of solvent cleaning operation. It's got 80 psi at the riser. That's a priority over a system that is that is maybe a machine shop that's got a 123 system and it's got 50 psi at the riser. That may actually cut it, but it may not. But in the scheme of things, in the world where you need to prioritize, it's far more important to prioritize the solvent operation with the grossly inadequate system over the machine shop that may have a slightly inadequate sprinkler system. The next video will be on the actual calculation, and then once we're done with pipe schedule, we'll kind of conclude with some thoughts, and then we'll begin to move on to the hydraulically calculated systems. In those, we need to take a step backwards and understand the concept of density, of design area, of different occupancy types. And once you're able to understand that, and we go through some of the more simple graphs, you'll be able to start pull some numbers out based on what's at the street from a water standpoint. So more to follow next month. Any questions or concerns, by all means, just post them. Thank you.